Hello and welcome to the third and last session of the Aerospace Workshop by SimScale and EUROAVIA. Yes, I'm very happy and glad to see again so many participants which want to listen to our today's lesson, and I think you guys already know the procedure. Before I actually start to dive in our today's topic, I just would like to make sure that everybody can hear me. So in the case you can hear me loud and clearly, please click the raise your hand button to show me that everything is working fine. Great, I already see some hands. Seems that everything is working. In the case, for some reason, the quality of the audio stream, for example, should drop, you can also use our toll-free audio service numbers. We have several numbers for several countries, and you just have to dial this number and enter the access code when you're asked. Great, then we can directly start to dive into our today's topic, and this session is about turbofans, which is very interesting, really interesting topic. And just to talk a little bit about the agenda, I will just give a very crisp introduction, first of all, to the concept of this webinar. We'll just talk about for 1 minute about some things a lot of people asked during the last week. And after that, we will start with our live demonstration, where I will first of all give you some fundamental insights to jet engines, how they are working, and also to some physical fundamentals we need to know about vibrations. And after that, I will show you also how to set up your own vibration simulation with SimScale, present your homework to you, and then we will have time for your questions. And I will try to answer them all. Great. Okay, then let's start. Just to make sure everybody knows about it, some quick facts about this webinar. Basically, as I mentioned, this is the final session. So the other sessions were already recorded, and you can watch them on our website. And just one thing I would like to talk about is the homework, are the homework assignments. We received a lot of homework assignment. At least more than 100 people submitted the homework for the first session. And in the case you have problem was finishing a homework exercise. For example, today at 12 p.m. is the deadline for the homework of session 2. And in the case you have a problem and maybe need a little bit more of time, just let us know, and we will decide from case to case where we can extend the submission deadline. And finally, if you have questions not only about simulation setup, but also about simulation in general or other things, you can also use the forum and the related category about this workshop to ask your questions and get help. Great, then let's start with our today's topic. And as I mentioned, today we want to talk about jet engines. But if you took a look at the description of our today's session, we want to talk about vibrations today. And therefore, first of all, let's make a crisp introduction what vibrations are from a physical perspective, and what does it, or how this is related to jet engines. First of all, if you take a look at the slide right now, you see different examples for vibrations and harmonic effect, and you may just did not realize it so far. For example, we have a pendulum clock here on the left side. We have a guitar in the middle, or what we can see on the right side are different displacement stages of a bridge. And as I mentioned, all these is somehow related to vibrations. And the exact reason is, if you think about it, at all these physical phenomena we are showing, we have a harmonic effect or periodical effect. At the pendulum clock, this pendulum is oscillating with a constant frequency from left to right. And in the end, this pendulum is used as a trigger for the clock itself to know the right time. A guitar is producing sound, and the way a guitar is creating sound is that the guy who's playing the guitar in the end is touching or moving the strings, and the strings start to vibrate with the same frequency like the sound we want to create. For example, if we want to have the A, we have a frequency of 440 Hertz, and then this vibration is conducted to the surrounding air, and we can hear it, what we call sound. And the final example, you may all know this video of a bridge in the army. A larger troop is going over this bridge, and they're going with this, and then because they are going uniformly, the bridge starts to vibrate and finally to crash. And we can simulate these effects, and they can have a big impact in industry and in physical applications. For example, if we think about an airplane in general, there we also have vibrations, and we don't want these vibrations to become too much. Or in the worst case, what happened with the bridge in the video I talked about, that we damage our machine or our airplane in reason of harmonic effects. And we can simulate this, and we have two kinds of simulations, or two kinds of analyses, which we have to perform therefore. First of all, what we call frequency analysis. A good example for that is the identification of eigenfrequencies and eigenmodes. When running a frequency analysis, I just want to find out at which frequencies are the eigenfrequencies of the part I want to investigate. An eigenfrequency is defined as the frequencies which are creating a resonance state. And once I have identified these frequencies, I can perform a harmonic analysis where I need these frequencies as the input and calculate the physical reaction through the application of a periodic oscillation with that eigenfrequencies. And to understand the physical importance, let's take a completely different example from all the workshop. This is a 3D printer, which is working a little bit like a milling machine, just the opposite way. Instead of removing material, we're adding material. And again, we have step engines which are moving parts with a very high speed and acceleration. The red parts you can hear are the step engines, and they're moving, for example, the parts on this rod. And if you would right now to do a analysis, let's say a frequency analysis of such a system, you don't have to simulate the whole system. You can only also isolate parts and take a look at them. For example, here we are just interested in the frame, because the frame is the relevant mechanical system for us. And then we can even reduce this frame just to this side piece by using symmetrics in an effective way. Okay, and what we would do here would be the same. Performing, for example, if we have this frame part here, identifying first the eigenfrequency of the frame, and then use these frequencies as an input for the harmonic analysis and calculate the physical reaction through the application of a force which is oscillating with the eigenfrequency of the frame. Okay, and when we are going to prepare such simulations, and this is again a good example, this is 3D printer frame, we have to do some other steps, additional steps. And if you take a look here, what is the difference between this assembly and, for example, the wing structure, the bracket we investigated last week? One main difference is that here we have an assembly made of multiple solids, in contrast to the bracket, which was made of one solid. And every time where you have a structural simulation and you want to simulate a design which is made of several solids, you need so-called contacts. And let's take a look what a contact is basically. Okay, just imagine we have our load case, and first of all, because of that we are isolating this part of the frame, we already know that for this inner faces of the holes here at this connecting parts, here and here, we will have like a boundary condition, a fixation, which is not allowing these faces to move. But we also have like interactions between the several assembly, because if we just take a look at this assembly, you can see it's made out of 6 different solids. We have For each rod we have on one solid, and we already merged the nuts and the bolts to this rod to simplify it, and we have these connectors. And these parts are made from different materials and not directly connected. They're connected through bolts. And therefore we have to describe how these different solids or bodies are interacting. This is what we call a contact. And let's just start with some examples. In this case, to define all contacts let's start with this top one. And here we have two parts. And one contact is between the outer face of the rod and the inner face of the hole of the connector here. We have the same kind of contact on the next side, and we have a contact between the sides, this yellow, this of the rod and the connector. And this kind of contacts we have to define for all three connectors, and then we have defined all kinematic, let's say, relationships between several parts. Great. Okay, and you may ask yourself, now what does it have to do with jet engines? And to get an idea about that, let's first of all take a look how an actual jet engine is working. And therefore, let's just start to take a look at different parts we have. First of all, how is a jet engine working? And basically, a jet engine is based on the third law of motion by Newton, which says, let's assume to make a good example what the third law is saying. Let's assume you have a balloon, and this balloon is open here. And then you have here an air jet, which is leaving this balloon. And here you have high pressure. Let's make P high. And in that case, the balloon will fly. And this is basically the same principle or equal principle like a jet engine, maybe more like a rocket. But the reason is that this leaving air jet creates a force, let's call it force A. And third law of motion of Newton says that if on a body is acting force, we have the same force in the opposite direction called Fb. And that's the reason why the balloon is moving. And in the end, what jet engine is doing is it's quite equal. First of all, we have here our combustion chamber. You can see here. Here will be the combustion chamber. And basically, what is the combustion chamber doing? The idea is that heating up the incoming air to a high temperature will expand it, and that will create a jet. Right. And for optimum and very efficient combustion, I need high temperature and high pressure of the incoming air. And therefore, I have here a compressor stage. And this compressor stage is in the end made of rotators and stators. And the rotating blades add energy to the fluid, which will increase pressure and temperature. Just to give you an example, inlet temperature is about 10 degrees Celsius, and the temperature for the combustion chamber is around 450 degrees and around 35 bar pressure. Great, okay. And then the question is, where do I get the energy for the compressing stage? And that energy is delivered by this part here, by this low pressure turbine, because the compressor as well as the turbine are mounted on one single shaft here. And this turbine the turbine blades have a special airfoil shape that generate lift and will turn the turbine and therefore the whole shaft. And in the end, here we have a part called fan, which was added later, not directly at the invention of the jet engine, but right today, every, I would say, commercial aircraft which a turbine has a fan jet engine. And this fan is used to increase the efficiency and performance of the jet engine. And what we will investigate is today, because sometimes you maybe hear about bird strike, what can happen is that a bird, another object, gets inside the turbine and can destroy or damage this first fan here. And this machine is a rotating, or this turbine is a rotating machine, rotating at high revolution number, several thousand revolutions per minute, and therefore their vibrations can have a negative impact on the reliability and the performance of a jet engine over the lifetime. And that is what we want to investigate today. We want to investigate in the end what happens to the vibrations of the engine if, for example, one or more blades of the fan are lost. And here you can see a CAD model of the full engine. So we have, again, here's the fan. We have the burning chamber, the compressor, the turbine. And to simplify our work, we will isolate first all static parts. So we will remove the shaft, the compressors, the rotors of the compressor stages, and this will allow us to perform a structural simulation regarding the vibrations. And the process will be that right now I will do a live demonstration with you. I will show you how to create the simulation, and first of all the frequency analysis. So first of all we will just investigate at which frequencies are the eigenmodes of this jet engine assembly. And first of all, as you know, we have to create a mesh, set up a simulation, and then we can do the post-processing. Okay, and then I would suggest let's just start. I have prepared a project here including only the geometry of the jet engine. And now let's open it. Great. By the way, guys, if you have questions, just let me know and write a message to the question box. Yes, and as you can see, the project was imported, and this model is made out of two solids, one for the jet engine assembly and one for the mount to the wing. Here you can check again dimensions make sense, 2 meter bounding box size for the whole engine. And what we will do right now is to create a new mesh. First of all, we therefore have to create a new mesh project, clicking on this Add New button. Click on this Add New Mesh button. Then we have to choose a CAD model as a base. We'll choose the jet engine model we have. Click on Save. We'll create a new meshing object. And next is to add a mesh operation to this mesh object. So we will choose in this case tetrahedral automatic, which creates automatically tetrahedral mesh based on 3 parameters you have to specify. And we are asked for the order of the mesh. And as you can remember, we need second order if we think that we will have massive deformations. And since we don't expect to have so high deformations, we can use the first order mesh. We want to have overall moderate mesh fineness, and we will use 8 computing cores to calculate the mesh. And that's all to generate the mesh. Just click on Save, click on Start, and the mesh will automatically be generated. By the way, I got a question by Christian. And Christian said that he cannot find his homework assignment for the second webinar. What can he do? Christian, listen, I would suggest just go on your dashboard. I can show it to you in the meantime. Just let's Google for SimScale. And if you log into SimScale, you can go on your dashboard. And here you can see your latest simulation jobs, for example. If you click on this, you will be forwarded to the project. If you click here on View All, you can see all projects which you have created and even search for them. In the worst case, Christian, just send me an email and we will find a solution to maybe extend the deadline for your homework submission. Great. As you can see, the mesh generation is already in process. And since it can still take several minutes, I've prepared a project including a finished mesh, but first of all, let's do a quick wrap-up. So I showed you how to open a project, which I think you already know, and how to perform the automatic tetrahedral meshing for a first-order mesh. Maybe just one thing to show, which I think is important. This model for sure needed to be prepared. So as you can see, it was massively simplified. We removed all screws, simplified shapes, closed on open edges. And so this is something we did not demonstrate during this workshop, but which is very important part of the work of simulation engineer, by the way. Right, and now let's go to the next step and therefore switch to the project I've prepared, including the mesh. And this project includes exactly the same mesh setting. And now you can see how the mesh looks like when it's computed. And yes, you can see that it was automatically refined, for example, in the area of the blades. Great. And now we're going to set up the simulation. Therefore, click on Switch to the Simulation Designer tab and click on Create a new simulation. And first of all, we ask what kind of simulation we want to perform. And as I mentioned, as a first step, we need the eigenfrequencies of our jet engine. Therefore, we will perform a frequency analysis first. Click on Save, and everything you need will be added to the simulation project tree here on the left side. Next, we have to specify which domain we want to use. So we select the mesh, click on Save, and the mesh will be added to the project. Right, that can take several seconds. Okay, and next step is optional. We will create topological entity sets. And as you know, we can use these sets to simplify our further work. And we will right now create 4 different phase sets, which we'll need later on. Let's start with the easiest. Later on we have to define a fixation. So this needs to be, the engine needs to be fixed somewhere. And we will just use this phase because this is later on connected to the wing. And we will choose these 2 faces, click on Create a set and call it fixation. And then we also will create a phase set where we'll later apply the vibrational load. And since this is transferred through the shaft and the bearings, we have to select this interfaces where the bearings are later on connected to. And yes, let's see if we have everything what we need. One second. I will hide just for 1 second. Sorry. Pylon. and select these two faces. And we have here again these two faces, 4 faces in total. Create a set, let's call it engine vibrations. And now we have to prepare our contact. Here we just have one contact because we have just only 2 parts. And let's prepare now which faces will be used as slaves and master. Basically, in most of cases, you can theoretically choose by yourself which faces will be or which part will be master and which slave. General rule is that master should be defined for those faces on bodies which will move less. And here, I mean this connection part, this pylon here, I think will not vibrate very much itself and therefore not move or displace very much itself. Therefore, we will create the master based on the engine and the slave on this fin. So let's start with a slave for the fin maybe. And let's just choose all faces which are in touch with the engine itself. And we just select them all. One second. Like that. Great. Create set. Call it just slave. And then recreating a kind of master slave for the opposite side. And here you can see again how the model was prepared during pre-processing. For example, everything is clean here. And don't be worried, we'll provide you with the exact list of all faces in the step-by-step tutorial. Here are some faces missing. For example, if you take a look, you also have to select this face, and the small faces. We can modify it by delete it and create it new. Okay. Great, then we are done and we can switch to the material definition. This time we will assume that both parts are made of aluminium, so we can access our material library. Choose aluminium, click on save and apply it on both volumes. And one thing I nearly forget is defining the contact itself. Therefore, we just call one so-called bounded contact. And as a master, we choose master. As a slave, the slave face set. And we will use a manual tolerance, which is used to detect if 2 faces are touching or not, of 1/10 of a millimeter. And basically, we now can start to define the boundary condition. You see that there are no initial conditions available for this type of simulation. The reason is they are not needed. And basically, we don't need really boundary conditions. The only thing, so we need no loads because the frequency analyzer is load independent. If we add a load, it will not change the value. We just need a fixation, so we'll go on constraint boundary condition, create a new one, and call it fixation, apply it on this phase set, and the setting means that this phase can not move in any direction. And finally, the only thing we have to update is our simulation control panel. We will use again 8 cores and not MSW, 20 eigenfrequencies. So the first 20 with the lower limit of 0 and the upper limit of 100,000 Hertz. Great. Now everything is done. And we can, if we want, for example, we can add additional solution fields, which is not necessary really in this case. And then we can just check our simulation. You can ignore this warning, just say that you will use only one CPU. You still should use 8 cores because 8 cores means more memory. Create a simulation, and then we can run it. Then let's just take a quick look at what we've done. I showed you how to set up the general simulation, including analysis type, how to create topological sets for slave and master phases, as well as for the fixation and the load, or the boundary condition. Then I showed you how to create contacts, how to define a material by accessing our SimScale material library, and how to define the necessary boundary condition and solve the settings. And once you start the simulation, it can take up to half an hour. And I have prepared for sure also a case including the result, and then we can take a look what the result actually is. Okay, so again, same simulation setup. And once the simulation is finished, first of all, you will see it took 15 minutes. The result is 2 GB right now. And if we, for example, now take a look at the solver log, you can see all the messages which were created by the simulation software itself. And if we go now on post-processor and on eigenfrequency plot, we can see the different eigenfrequencies, the first 20. So this is eigenmode 1 to 20. And you can see we have eigenfrequency at 13.57 Hz, 17.36 Hz, and you can even take a look at the table, which is more comfortable. These are all the first 20 eigenfrequencies. And we will use later this information to investigate what happens in the region of eigenfrequencies. Just imagine, we know that our engine will be operated a lot of time with a frequency between, let's say, 140 and 160. Then we would like investigate these 3 eigenfrequencies. Okay, great. And yes, you can also take a look theoretically at the eigenmodes, but which are not really giving you information in most of the cases. Great, then let's do a wrap up. Thank you. Yes, or before I say thank you, first of all, let's really do the wrap up. So as you saw, the frequency analysis will give us information about the eigenmodes, and that is, by the way, I think a good introduction to your homework, because your homework will be to investigate the harmonic effects of this jet engine, and it's made of several parts. The first part of the homework is for you to create the same frequency analysis I created, and then to modify or to create a harmonic analysis based on the frequency analysis for the whole jet engine, and for a jet engine with a missing 1 blade, and for the jet engine version with 2 blades missing. And the good thing is you just need 1 mesh. You will remove these blades by adding sensible boundary conditions. And on our SimScale website, simscale.com/aerospace-workshop, there you can already find all the resources you need. Oh, wait. Wrong workshop. Here. The recording of our today's webinar will be uploaded to tomorrow at lunchtime, and you can already find here the step-by-step tutorial, where you will find all information you need. Okay, great. That's the homework, and now we have a lot of time for your questions and answers. Oh, seems like PowerPoint crashed. Just wait a second, sorry. In the meantime, do you have questions? I have a first question by Anwar, and he just wants to know if we can use the frequent simulation IC engine crankshaft to determine the mass of the flywheel. Basically, yes, that would be possible. As I got you right, Anwar, your idea is to investigate the eigenfrequency of the whole engine, or of the, I think maybe of the main shaft, and to determine the mass of the flywheel. You can simulate that, but I think it's more straightforward to calculate the weight of the mass wheel based on a simple analytic solution. So if you just, with pen and paper, model this yourself and calculate this yourself, because the vibration of the shaft itself is not the main effect here. Okay, and there is a question by Kevin. He wants to know if there's a way to watch the previous webinar, the one that started at 4 p.m. Kevin, first of all, we postponed the webinar today because we got, just to let you know, as most of you know, we will have guest speakers from Airbus Group joining us, which will show us how simulation is used at Airbus. And this webinar was postponed because a lot of people said that they have no time today, but they would like to join to the live session. And therefore, we will reschedule this webinar and invite you all participants and registrants of the Aerospace Workshop to this exclusive webinar. And I think I will send out the invitation for the workshop next week. It will take place the week after next week. Okay, great. Are there any more questions? No, seems not to be the case. And thank you very much. It was a great time I had with you. I hope you learned some interesting things. Please, guys, you have still the chance and some time. Submit your homework, and you will receive the certification as well as the instructions how to join the professional training up to 2 or 3 weeks after the last homework submission deadline ends. Thank you again very much. Have a nice week and hope to see you soon. Bye.